Hello everyone, myself Sagmar. Now I am here to give a seminar on radar engineering, and the topic is radar receivers. Now I am going to discuss about what is a receiver and what is a radar receiver. The receiver section is connected to the antenna by the duplexer. The receiver section is super heterodyne type and it consists of a mixer, IF amplifier, detector and the VD amplifier. Here mixer is used to combine the signal from the receiver. Mixer is used to combine the signal from the receiver and the local oscillator. There is some more differences. IF amplifier is used to amplify the IF signal, and detector is used to detect the signal, and video amplifier is used to amplify the video signal. The first stage of the receiver is usually an RF amplifier with very low noise properties. The RF amplifier is followed by the mixer of fairly low noise figure. The mixer is a crystal diode which is fed to the IF amplifier. The IF amplifier operates at 30 and 60 MHz at nearby frequency. So here IF stage provides most of the receiver gain. It is the most important stage, and the IF receiver should be a low noise device to ensure that overall noise figure of the receiver doesn't deteriorate to great extent. Next, the down conversion from microwave frequency to IF frequency may be done in number of stages to ensure adequate image frequency compression. The detector is crystal diode whose output is amplified by video amplifier having the same bandwidth as the IF amplifier. The output signal is then fed to display unit, which may be a CRT, that is cathode ray tube. Here the CRT may be used as A scope, PPI, A scope, plan position indicator, or A scope, B scope, C scope, and D scope, E scope, etc., which can be used as the CRT displays. Next, let me discuss about what are the characteristics of the radar receiver. The first one is the function of the radar receiver is to detect the desired echo signal in the presence of noise, interference, or clutter. It must separate wanted signals from unwanted signals and amplify the wanted signals to a level where target information can be displayed to an operator or used in an automatic data processor. The design of the radar receiver will depend not only on the type of the waveform to be detected, but on the nature of the noise, interference, and clutter echoes with which the desired echo signals must compete. Noise can enter the receiver via antenna terminals along with the desired signals, or it may be generated within the receiver itself at the microwave frequencies usually used for radar. The external noise figure which enters via antenna is generally quite low. The measure of receiver internal noise is the noise figure. So noise figure, from this point, noise figure is defined as the SNR of input by SNR of output. Obviously, the receiver should be designed to generate as little internal noise as possible, especially in the input stages with the where the desired signals are the weakest. So the receiver must be designed where the internal noise should be very low. Next, coming to next point, receiver design also must be concerned with achieving sufficient gain, phase and amplitude stability and dynamic range, tuning and ruggedness and simplicity. So receiver must be designed with all these properties. Protection must be provided against overload or saturation and burnout from nearby interfering transmitters. Timing and different signals are needed to properly extract target information. Next, receivers that must operate with a transmitter whose frequency can drift need some means of automatic frequency control, AFC. Radars that encounter hostile countermeasures need receivers that can minimize the effect of such interference. Thus, there may be many demands placed upon the receiver design in meeting the requirements of modern high-quality radar systems. Although the super regenerative crystal video and tuned radio frequency receivers have been employed in radar systems, the super heterodyne has been almost inclusive application because of its good sensitivity, high gain, selectivity, and reliability. No other receiver type has been competitive to the super type. Let me discuss about now the receiver noise figure. Noise figure of a receiver is a measure of noise produced by the practical receiver as compared with the noise of the ideal receiver. It can be given as Sn by In by S out by N out. It can be classified as N out by Sin by S out into N in. N out by S out by S out into N in can be written as K T naught Bn into G, where Sin is the available input signal noise power, Nin is the available input noise power, S out is the available output signal power. Next, N out is the available output noise power. Available power refers to the power which would be delivered to a matched load. The available gain is equal to the S out by Sin, where K is the Boltzmann constant and T is the standard temperature and Bn is the noise bandwidth. The product KTN is equal to 4 into 10 power 21 watts per megahertz. The purpose of defining a standard temperature is to refer any measurements to a common basis of comparison. The equation above permits two different but equivalent interpretations of noise figure. It may be considered as a degradation of signal to noise ratio caused by the network, or it may be interpreted as the ratio of the actual available output noise power to the noise power which would be available if the network merely amplified the thermal noise. The noise figure also given as Fn is equal to Kt naught Bng plus delta n by Kt naught Bn into G, which is written as 1 plus delta n by Kt naught Bn into G, where delta n is the additional noise introduced by the network itself. Next, coming to the noise figure of networks cascade, let there are two networks with gain and noise figure F1G1 and F2G2 and same bandwidth Bn. Our aim is to find the overall noise figure. Next, from the definition of noise figure, the output noise number of two circuits in the cascade is given by N naught is equal to F naught Nn is equal to Fn G1 G2 Kt naught Bn is equal to noise from network 1 at output of network 2 plus noise delta 2 introduced by network 2. Kt naught Bn F1 G1 G2 plus delta 2 is equal to Kt naught Bn F1 G2 plus F2 minus 1 Kt naught Bn G2 is equal to, which is written as F1 plus F2 minus 1 by G1. Next, coming to extending the same method of noise figure of n networks, F1 plus F2 minus 1 by G1 plus F3 minus 1 by G1 G2 plus and so on Fn minus 1 by G1 G2 and so on Gn minus 1. This is known as radar. This is what about radar receiver and characteristics of radar receiver noise and the noise figure of the networks in cascade. Thank you.